Okay, so today we're going to talk about graphical models a little bit more. It's going to have some overlap with last week's recitation, but I felt like since it's sort of important material that it was worth going over some of this independence structure and sort of inference in Bayesian networks again. So basically I'm going to work through an extended example using this graphical model that is projected on the screen. So feel free to stop me and ask questions if you're confused about anything. But why don't you start by sort of looking at that graphical model. And so basically, let's suppose we have these 1, 2, 3, 4, 5, 6, 7 variables. And it's this model of how like these two diseases, flu and dehydration, relate to these various other variables, including season and then a bunch of symptoms, right? And let's suppose that we also have a bunch of conditional probability distributions for each of the variables, and we'll assume that the variables are all binary for now. Although, in the first thing we're going to do, which is try to like understand what independencies exist among these variables, the conditional probability tables don't really matter. Okay. So since this is sort of an example, feel free to I'm going to try to get people to answer a few questions that I ask. Okay, so thinking about deseparation, baseball, however you like to think about it. Let's start with is season independent of chills? Okay, so I'll give you 30 seconds to think about it, and then someone hopefully will raise their hand. So nothing is observed. So I'm just saying, is season independent of chills? So is it true or false? Is it dependent or not? Dependent, right? So it's clear to say it's not independent. Okay, because in fact, all we can say from this network is that we don't know for sure that it's independent. We actually don't know if it's dependent or not until we actually see the conditional probability tables. But from the structure of the network, all we can say is that they're not independent. And can anyone point out a path along which influence can flow from one to the other? Can you speak up? Yeah, exactly. Okay. Okay, what about if we observe the flu? Can't hear you. Someone raise their hand.
Independent?
Yeah, so it's independent. So why?
Because if you have information on flu, you don't have to go back to season. You can directly. If you have information on flu.
Yeah, and basically, the only path from season to chills is directly through flu, right? So that's the only path we need to look at, and we can see that based on the different 3 variable structures that we know about and how influence flows through them, we can see that if flu is sort of blocked, you can't get from season to chills, right? Okay. What about this one? Is season independent of headache given that we observe the flu? No. Okay, why? Yes, exactly. So influence can still flow along the path season through dehydration and to headache, right? So when we observe flu, one path is blocked, but a second path is still open, so they're not independent, right? Okay. What about if we also observe dehydration? They're independent, yes. So basically that other path that we were relying on is now blocked and there are no other viable paths, right? Okay. What about this one? Are season and nausea independent given that we observe dehydration? Why?
Because you can go through flu, headache, and dizziness, and so it will link to numb and
Yeah, exactly. Okay. What if we also observe headache? Are season and nausea independent? Okay, yeah, they are. So season to nausea, how many different paths are there? 1, 2, I sort of see at least like 3, right? 3 distinct paths. But when you observe dehydration and headache, if you look at every individual path, you find that they're all blocked. Therefore, they're independent. Okay? What about this? Is flu independent of dehydration when you don't observe anything? Why not? Flu independent of dehydration. Yep. Well, can influence flow through headache? No, because that's a V structure, right? Influence can only flow through a V structure when the central node is actually observed. That's the one that's different from all the others and that you should keep in mind. But season is not observed, so we can go up through season and back down to dehydration, so they're not independent. Okay, same question, but let's suppose we observe season and headache. Are they independent? Are flu and dehydration independent?
no.
Why?
When the headache is observed, you can go through it and then you can
Right, so as I said, in this special type of structure, when headache is observed, that's actually when influence can flow down through headache and back up to dehydration, right? Because they have a common child. Okay, what if we just observe season? Are they independent? Yes, so this is the case in which flu and dehydration do become independent. So if we observe season but don't observe headache, now they're independent. Okay. So if you observe season and nausea, are flu and dehydration independent?
Yeah, because you can go through the headache, dizziness, and because nausea is observed, so can go through to the dehydration.
Yeah, that's right. So they're not independent. You can go through that one path that was just specified. Headache, dizziness, nausea. Okay. What about, is chills independent of nausea when you don't observe anything?
Not independent.
They're not independent. Okay, so you can probably all find a path along which influence can flow. Okay, this is the last one. Is chills independent of nausea given that we observe headache? Still no. Okay. So in that particular case, when we observe headache, one way that influence can flow from chills to nausea is through flu, headache, dehydration, and then nausea, right? Okay. So now let's talk about how to estimate some probabilities for the graphical model, which you got some practice with in your homework, but I thought it was worth reviewing this stuff because I got some questions about it in office hours, and also because questions like this are very likely to appear on your test next week. Okay. I'll just erase this. Okay, so first of all, let's suppose we want to write the factorized form of the joint distribution, okay? So here I'm using, I think Z represents, so S is season, F is flu, D dehydration, C chills, blah, blah, blah. The only one that's strange is Z represents dizziness because we have two Ds. So does anyone want to come write down the factorized form of the distribution? You look good over there. Look like you want to do this? No? Anyone else? It's not too hard. Come on, brave volunteer. You want to do it?
Sure.
Great. Okay. All right. So looking at the, here's a printout if you want to look at this. Okay. So when we do this, start from the top, right? Which you did. Probability of S has no parents, so it doesn't depend on anything. So we just write probability of S. Then we have flu, whose only parent is season, so we have F given S. Dehydration also has one parent, season. Chills. Yep. Yes. So headache has two parents, so you have to include them both, right? Oh, make a laptop. Okay. Perfect. Good job. Thank you. Okay. So it's very easy to just remember how to write down the factorized form of the distribution by looking at the graphical model, right? You just write, you take each node, you look at its parents, and you write, it's a big product of the probability of each node given its parents. You can also, if you for some reason forget how to do this, you can also derive this from the chain rule and the independencies that you can read from the graph, right? But that kind of takes a while, so it's easier to just sort of remember how to do this, and it'll be very useful for doing things like what we call performing inference, which can be as simple as sort of manipulating probabilities in order to calculate some value that we can't read directly from the conditional probability tables that we have, right? Okay. So let's suppose you want to calculate the probability that someone has the flu when there's no prior information is known. Okay? So mathematically, can anyone tell me what this sort of translates to? What probability statement do we want to evaluate? Yeah. Yeah, P of F equals true specifically, right? Because it's the probability that you do have the flu. So here are a bunch of conditional probability tables, and basically each of these corresponds to one element in this big factorized distribution. So do we have any conditional probability table that directly tells us the probability that F equals true? No. So we need to sort of figure out how to express that in terms of the others that we do have, right? Okay, so how do we do that? So let's look for a conditional probability table that does involve flu. Well, there's one sort of toward the top that involves flu and season, right? So let's use that one. Okay. So the first thing we'll do is sum over all possible values of season so that we can use sort of marginalization to rewrite probability of F in terms of the joint probability of F and S. So here, this is the joint probability that flu is true and that season is this little value, little s, right? Which can take either true or false. Okay. Next, we can use the chain rule to write this in terms of So this allows us to write the joint probability in terms of the conditional probability of flu given season, which conveniently we have, right? And the probability of season by itself, which also we conveniently have, right? So now we're pretty much done. All we have to do is like manually calculate this value, which would entail summing over the values true and false for season, right? So ultimately this would look something like this. So the expression evaluated at season equals true plus the same expression evaluated at season equals false. Nope. Right? And then I'm not going to calculate the actual numbers, but you get the idea. So that was actually pretty easy. That was a pretty simple one, but you can use a similar approach, basically like different combinations of laws of probability that you know, chain rule, marginalization, definition of conditional probability, etc., Bayes rule, to evaluate pretty much any probability that you would want to possibly evaluate, right? So let's do a few more examples. Okay. So what if I want to know the probability that someone has the flu given that it's winter? So I can write that as probability that flu equals true given season equals winter, right? Okay. So this one, do we have to do anything? No. We can just, what's the probability? Somebody tell me. 0.4. Okay. What about if we want to calculate the probability that you have the flu given that it's winter and you have a headache? So now we condition on a second thing, right? So suddenly this becomes like actually more complicated to work out. Okay, so given that we want to evaluate this expression, can anyone suggest a good first step? Yeah. Yes, and what is that called? I would call that the definition of conditional probability, basically. Yeah. Okay, yes, so this is very frequently a great first step to take. So now we just have like these two, like we can evaluate the numerator and denominator separately and then divide and we'll be done, right? So let's look at and actually in fact, like one thing to notice is the denominator, we can rewrite that using marginalization so that it's equal to the numerator but summing over a third variable, which is the flu, right? So then it's even easier because we really only need to evaluate the numerator and then sum over these two different instances. So let's write that out first. Okay, so again, this is usually a good second step to take. Yeah, question?
But why would F then false?
Oh, yeah. We can call this something else, x. I meant just like any value, generic value. Usually use like the lowercase letter to represent some value, but in that case it was ambiguous, so yeah. Okay, so like I said, these are two good steps to remember. Now we just have to basically evaluate this expression, and then we can plug in and we'll be done. I think I'll just go over here. Okay. So one thing to notice, one thing to keep in mind is like when you have, so here we have a joint distribution, and you might be tempted to apply like the factorization that you use to get the original factorized distribution to this small distribution. Don't do that. You can only apply, like the only reason it works for the whole graph is because by the chain rule, because like I said, the graphs are sort of constructed in that way, such that you can pull these properties out of the graph. But once you're faced with like a smaller joint probability, you need to only use known laws of probability to evaluate that. Okay, so does anyone have a suggestion for a next step to evaluate this? We have flu season, and headache in this expression.
You can marginalize it further
Yeah.
and add
What would you add?
that variable.
Which one?
Dehydration.
Yeah, the D. Yeah, dehydration. Yeah. Okay, so now that we have this, it turns out that it's a good time to apply the chain rule. Okay, so let's say we want to pull out headache first. H equals true, M equals true, D equals true. So headache, okay, so you can see the conditional probability table for headache, right? Yeah.
Why do we sum for only dehydration, not all other variables?
Because it turns out that that's the only one we need to sum over in order to be able to use the, because okay, so ultimately our goal is to get an expression that's just in terms of what we have, like probabilities that we have in one or more of these tables, right? You could actually marginalize in every variable, right? And then you would have the full joint distribution, and then you could write it in its factorized form, and then you could do this. But that's often a lot more computation than you actually need to do. So your goal is to sort of include as few variables as possible to get you to a joint probability that you can write in terms of just the conditional probabilities. And like it just turns out for this one that D is all we need. And if you think about it a little more, maybe like if I hadn't told you that, you would think about it a little bit and you would have figured it out. Yeah, okay. So we want to get headache on the left. So we want to have one expression that's headache given F and D, right? But if we just apply one step of the chain rule, we get headache equals true given this would be our first term, right? So, but we don't want season in there. So what can we do? Yeah.
You can just rewrite it without season because it's conditionally independent given flu and headache.
Exactly. So headache is conditionally independent of season given flu and dehydration, so it's like totally superfluous that we even write that there, so we can just drop it. That's gone. Okay. So now the second term here would just involve season, headache, and dehydration, right? But let's say we want to do another step of the chain rule to like sort of factorize that further. So let's say we do, can people still see this? Probably not. Maybe I'll just go over here. Okay, so I'll just rewrite this without season. So let's say next we want to pull out, so here we're left with and we want to apply the chain rule again here. So let's say we pull out flu. So then we're going to rewrite this as flu given S and D, and then times the probability of S and D. But we, again, have this same problem here, right? We just want flu given season. So can we do the same thing and drop D? Yes. Anyway, so we keep doing this basically, and we get like the full factorized form is so it turns out like the left-hand side is equal to the right-hand side, and the right-hand side is in terms of a product of our conditional probabilities. So now we can just plug in and calculate the original thing. Okay. So I think that's probably enough. That sort of gives you a good example of how to do these types of problems. So the next thing that I sort of wanted to briefly go over is how to do maximum likelihood estimation or map estimation for Bayesian networks. Do people want to see that or not really? Yeah? Okay. Okay. So in this case, I gave you, like the model is sort of fully parameterized, right? Because I gave you all of the completely filled in conditional probability tables. But in some cases, you may not have all of your parameters given to you, or you may not have good estimates of them ahead of time. So you might want to estimate some of the parameters in these tables. So if your variables are binary, let's say, like they are here, this stuff is actually pretty easy to estimate using maximum likelihood estimate. Let's suppose you just wanted to estimate the probability of that season equals winter. And I give you a bunch of data. And each data point has a value for each variable, right? So like one data point could look like the season is winter, flu is true, dehydration is false, et cetera, et cetera. How would you calculate the maximum likelihood estimate of the probability that season is winter from that data? So keep in mind, the probability that season equals winter, if we think of like winter as true and summer as false, then it's sort of like the parameter of a Bernoulli distribution, right? Yeah.
Do you have all the 7 parameters in the data point?
Let's assume, yeah, everything is observed, or like we have no missing data.
Average,
Right.
average number of
Right, so you just look at the number of samples where season equals winter, and then divide by the total number of data points. And that would be like your Bernoulli maximum likelihood estimate. So let's suppose now we want to calculate the probability that flu equals true given season equals winter. Again, with the MLE. Does anyone have?
All the data points where S is equal to winter, then find which cases it goes to divided by that.
Yeah, so like again, it's the same idea except that you're doing maximum likelihood estimate sort of for a conditional distribution. So you're going to count up the number of cases where you have both flu equals true and season equals winter, and that's your numerator. And then your denominator is the total number of cases where season equals winter, right? So it's sort of like if you apply the definition of conditional probability, it's the joint over whatever you're conditioning on. It's the same idea except applying this to the concept of maximum likelihood estimates for Bernoulli distributions. You could also have a prior over each particular like Bernoulli distribution, and then you would use the formula for the map estimate for a Bernoulli, where you incorporate the pseudo counts, right? Depending on what exactly your prior is. But if it's a beta prior, you would incorporate those pseudo counts and sort of do the same calculation. So when your data is fully observed, which is the case I'm talking about, this type of stuff is pretty easy. When it's not fully observed, it gets more complicated, and you have to do something like EM for inference. But I don't think I'm going to talk about that today, since I don't think that it was discussed in a ton of detail in lecture. So yeah, does anyone have any questions about that? Or about this? Or Bayes nets? Okay. Does anyone have, yeah? So an example of the map estimate, and what did you say?
Like, for example, you apply map estimated, like, apply probability here. Like example.
Yeah, I mean, so like when you're doing a map estimate, it's usually because you have a prior, right? So let's say we want to calculate the probability that flu equals true given season equals winter. And let's call that P flu given P flu given winter, right? Which represents the probability that flu equals true given season equals winter. 1 minus this would represent the probability that flu equals false given season equals winter. So this is sort of the parameter of a Bernoulli distribution, right? So we can apply a prior, like a beta prior, which is what we used when we were previously applying priors to Bernoulli distribution, to Bernoulli parameters. So we can put a beta prior over this P, right? And if you recall from when we learned about map estimates, when you have a beta prior over the parameter of a Bernoulli distribution, the map estimate is basically so the MLE estimate would be this. Count of the number of cases where flu equals true and season equals winter divided by count of season equals winter. If we had a prior, then we would ultimately, the final formula would be similar to this, but with like some number of like pseudo counts. And then similarly here, right? And the number of pseudo counts that you use in the numerator and denominator depends on the parameters of your beta distribution. And I don't recall the exact formula off the top of my head, but it's something that's, you can look it up in the lecture from when we were talking about map and MLE estimates. But it's the same principle here. So you can easily apply a prior to any parameter in your model that you want to estimate.
What if the distribution is not a graphical distribution here?
Yeah, so if you had like a continuous valued variable, you could have a Gaussian distribution. And then you might want to estimate the mean of that Gaussian. And then you could still apply a prior over the mean of the Gaussian and use that prior in deriving your estimate, your map estimate. Yeah.
When you're running the base control, right? So you're deciding that it's better to say that it's not independent rather than independent. As I don't know, that was two states, right? They would say.
Well, so let's say you're just given the structure of a Bayesian network, right? Like you don't even have the conditional probability tables. Then really all you can say is that two variables are definitely independent or not. But let's suppose you can't read from the structure that they're independent. You could still construct the conditional probability tables such that they actually are independent, even though like there's an arrow between them. It's just that the structure guarantees that you can't make them dependent, no matter how you design your conditional probabilities. Does that not make sense? So like, what's a better way of saying that? Like, you know, the traditional definition of independence is that the joint probability factorizes into the product of, like, probability of x comma y factorizes into probability of x times probability of y, right? So really, to test for independence, that's what you would test. You would write out, like, the full joint distribution and try to determine whether, you know, whether that holds. What Bayesian networks tell you is that certain independencies are guaranteed based on the structure of the network. But it's sometimes still possible to have more independencies than that, right? It's just that those aren't guaranteed by just the structure of the network. That's all. It's a sort of minor point. I wouldn't worry too much about it, yeah. Other questions? EM? Yeah. So, hold on 1 second. So I think I'll just turn this off. Okay, so I was just talking about how to do basically when you're talking about a Bayesian network, estimating probabilities is sort of called inference, and estimating parameters in your network is generally called learning, right? And I was just talking about how to perform learning in Bayesian networks when your data is fully observed, right? Which means like for each sample you have a value for every single variable. But if you don't have that, it's a lot more difficult to perform learning or parameter estimation. So one method to do this is an algorithm that was talked about in class called expectation maximization, or EM, right? And this is basically an iterative algorithm. So E and M are the two steps that you perform on each iteration of the algorithm. So basically, so the E step, where E stands for expectation, so in the E step, you basically calculate the expected value of your sort of hidden variables given what you have observed. And in the M step, you perform maximum likelihood estimation, but you sort of substitute in the expected values of the hidden variables for where they in the places where where their actual values would normally appear, basically. That's the general idea. I guess I don't really have time to go through an example, and I also didn't prepare one, so I probably wouldn't be able to explain it that clearly, just off the fly. But if you work through an example of EM, it makes it really clear like how you use the expected values of the variables in the maximization. And I feel like that's sort of the best way to really learn EM. So if you want to learn more about it, I would find a tutorial that works through a concrete example. But it's like a very common approach, like a very popular algorithm, although maybe not always the best choice, but it's popular. But yeah, I don't know, sorry, that's not a great in detail explanation, but that's sort of the overview. Okay, anyone have other questions about graphical models? Yeah.
Can you talk about the question at the end of the first class PowerPoint, at the end of the first class PowerPoint, there are 4 questions.
Okay, about decision trees?
Yeah.
Well, yeah, sure. I mean, so question 3, why use information gain to select like the next attribute to split on for your decision tree? That was sort of addressed in one of your homework assignments, right? Like you considered using just the error as the splitting heuristic and discovered that that doesn't always like predict the future that well. Like you might sort of stop splitting too soon if you use the error because, you know, like one split wouldn't reduce the error at all, but it would reduce the entropy, which, so like if you were splitting on the error, like if you have very few examples of one kind, which I think was the case in that homework question, and you split on the error, then both, like just at the top, the root node splits on a particular feature that's selected based on minimizing the error. Then the 2 child nodes would still both have the same label, so you're not going to reduce the error at all. which means that maybe you would actually stop splitting if you were just using that criterion, right? Then that doesn't really get you very far, but if you use the entropy, it does actually reduce the entropy. So you would, or yeah, no, maybe you wouldn't actually stop splitting, but you wouldn't necessarily, like all the features were equal, right? Because none of them reduced the error, but some of the features that later on could lead to a better result did reduce the entropy. So it led to, right, so entropy led to like a better selection of features because sometimes the entropy is reduced even though the error is not reduced. In terms of other criteria that you could possibly use, I feel like error is sort of the most natural one you would think of. So that's like what you might try to compare it to. In terms of learning, question 4, I mean, you can think of a decision tree as sort of a big if-else statement. So I'm not sure exactly how they would differ, but maybe it's sort of a top-down way of learning a bunch of like if-then statements, right? What is the set of decisions? I mean, in terms of the others, I don't know. Is there a reason you want to like hear about these? I mean, I think it's just sort of an exercise in thinking about these algorithms. I don't know that there's like a concrete answer to these questions. Like why not do an exhaustive search? I think that would, first of all, be more computationally intensive. If you're doing top-down, you can stop earlier, right, using these heuristics. You could probably think of other reasons. Yeah, I think they're just sort of intended as mental exercises. Okay, well, I think we're out of time, so we'll stop.